If the angles A, B, and C of a triangle are in an arithmetic progression, and if A, B, and C, lowercase a, b, and c, denote the lengths of the sides opposite to the angles A, capital B, and capital C respectively, then what is the value of this expression right over here? So let's see if we can work our way through this. So let's just draw the triangle just so we have a visualization of what all of the letters represent. So we have the angles A, B, and C. So let me just draw them like this. So we have the angles A, B, and C. And then the sides opposite them are the lowercase version. So the side opposite to capital A is lowercase a. Side opposite to capital B is lowercase b. And the side opposite to the angle capital C is lowercase c. Now, the first piece of information they tell us is that the angles capital A, capital B, and capital C of the triangle are an arithmetic progression. Arithmetic progression. Very fancy word, but all an arithmetic progression is a series of numbers that are separated by the same amount. So, and let me give you some examples. So 1, 2, 3, that's an arithmetic progression. 2, 4, 6, arithmetic progression. We're separated by 2 every time. I could do 10, 20, 30. Also an arithmetic progression. These are all arithmetic progressions. So all they're saying is to go from angle A to angle B, however much that is, it's the same amount to go from angle B to angle C. So let's see what that tells us. What that tells us about, or maybe it tells us, maybe it doesn't tell us anything about those angles. So if we could say we have angle A, and then we have the notion angle B. So we could say that B is equal to A plus some constant. We don't know what that is. It could go up by 1, it could go up by 2, it could go by 10. We don't know what it is. So A plus n. And then C would be equal to B plus n, which is the same thing, as B is A plus n. So this is A plus n, which is equal to A plus 2n. So what does that do us? Well, the other thing we know about three angles in a triangle is that they have to add up to 180 degrees. So this, and this have to add up to 180 degrees. So let's try it out. So we have A plus n plus A plus 2n plus A plus 2n is going to be equal to 180 degrees. We have 1, 2, 3 a's here. So we get 3a plus, we have 1n and then another 2n. 3a plus 3n is equal to 180 degrees. Or you can divide both sides by 3, and you get a plus n is equal to 60 degrees. So what does that tell us? Well, a could still be anything, because if n is 1, then a is 59. If n is 10, then a is going to be 50. So it doesn't give us much information about the angle a. But if you look up here, do you see an a plus n anywhere? Well, you see it right over here. B is equal to a plus n. And we just figured out that a plus n has to be equal to 60 degrees. So using this first piece of information, we were able to come up with something pretty tangible. B must be equal to 60 degrees. And you could try it out with a bunch of numbers. These could be 59, 60, and 61. That's an arithmetic progression. And once again, B is the middle one right over here. These could be 50, 60, and 70. Could be 40, 60, and 80. But no matter what the arithmetic progression is, in order for these three angles to add up to 180, the middle one has to be equal to 60 degrees. So that was we're doing pretty well so far. So let's see what we can do with the next part of the problem. And I'm trying to save some screen real estate right over here. Okay, so they want us to figure out the value of the expression a over c sine of 2c, capital C, plus c over a sine of 2a. So let me just write it down. So we have, I'll do it in blue. A over c sine of 2 times capital C plus c over a sine of 2 times capital A. What's that going to be equal to? So whenever you see stuff like this, you got a 2 here, a 2 here. Frankly, the best thing you should do is just experiment with your trigonometric identities and see if anything pops out at you that might be useful. And a little bit of a clue here. The first part of the problem helped us figure out what b is. it helped us figure out what b is. But right now the expression has no b in it. So right now this information seems kind of useless. But if we could put this somehow in terms of b, then we'll be making progress because we know information about angle b. So let's see what we can do. So the first thing I would use is, well, sine of 2a. So let me just rewrite each of these. So I should say sine of 2 times anything, that's just the same thing as, I think this is called the double angle formula. So this is, although I might be wrong there, I always forget the actual names of them. But sine of 2 times something is 2 sine of that something times the cosine of that times the cosine of that something. And you'll see that in any trigonometric book on the inside cover, or even a lot of calculus books. And let's do that for the same thing right over here. So sine of 2a over here is going to be 2 sine of a cosine of a. That's just a standard trigonometric identity. And in the trigonometric playlist, we prove that identity. I think we do it multiple times. And then out in front, we have our coefficient still. We have a over c times this plus c over a times this. Now, is there anything we can do? And remember, in the back of our mind, we should be thinking of how can we use this information that b is equal to 60. So if we can somehow put this in the form, get a b here. And when I think about how do you get a b here, I think, well, we have a triangle here. So the things that relate the sides of a triangle, especially when it's not a right triangle, is we're either going to deal with the law of sines or the law of cosines. And the law of sines, let me just rewrite it over here just for our reference. So the law of sines would say sine of a over a is equal to sine of b over b, which is equal to sine of c over c. And it looks like we might be able to use that. And let me just write the law of cosines here, just in case it's useful in the future. So the law of cosine, c squared, it's really the Pythagorean theorem with a little adjustment for the fact that it's not a right triangle. So c squared is equal to a squared plus b squared minus 2ab cosine of c, of capital C. So it's law of sines and law of cosines. So let's see if we can somehow use both of these to put these in terms of b, which we have information about. Well, the first thing is, I could rewrite this. So this says sine of c over c, and this is sine of a over a. So let me do that. So let me do this. So I have the 2a, I have 2a cosine of c. Let me write that separately. So I have 2a cosine of capital C, and then times sine of c over c, times, I'll do that in white, sine of c, that's a capital C, sine of capital C over lowercase c. That's that term and that term right over there. And then to that, I'm going to do the same thing over here. I have 2 times, I'm going to separate these guys out. Actually, no, I want to do the signs. So I'm going to separate this guy and this guy out. And so I get plus 2c cosine of a times sine of capital A over lowercase a times sine of capital A over lowercase a. Now, what did this do for me? Well, look at the law of sines right over there. I have sine of c over c. That's that over there. And then I have sine of a over a. That's that over there, capital A over lowercase a. They're both equal to sine of b over b. So we're making progress. We've started to introduce b into the equation, or the expression, and that's what we actually have information about. So this could be rewritten as sine of b over b. So this is the same thing as sine of capital B over lowercase b. And this is the same thing as sine of capital B over lowercase b. And they're both being multiplied, or both of these terms are multiplying, are being multiplied by that. 2a cosine of capital C times that, and then plus 2c, it's a lowercase c, cosine of capital A times that. So we can factor out the sine of b over b. So let's do that. Let's factor it out. So this is the same thing as 2a, and I already have a sense of what the next step is, so I'm going to leave a little space here. 2a times cosine of c plus this, and these are being multiplied. I left some space there. Plus 2c, 2 lowercase c, times the cosine of a, and all of this times the sine the sine of b over b. And we already know that b is 60 degrees, so we can evaluate this pretty easily. But let's just continue. See if we can somehow put this right over here in terms of b. Well, if you look over here, we have 2a cosine of c, 2c cosine of a. It's starting to look pretty darn close. Pretty darn close. Each of these terms look pretty darn close to this part of the law of cosines over there. And actually, let's solve for that part of the law of cosines to see what we could do. So if you add 2ab cosine c to both sides, you get 2ab cosine of capital C plus c squared is equal to a squared plus b squared. Or if you subtract c squared from both sides, you get 2ab cosine of capital C is equal to a squared plus b squared minus c squared. And this is interesting. And we can switch around the letters later on. But this looks pretty darn close to this. So what if, and this looks pretty darn close to this, except we're dealing with an a instead of a c. We've just switched the letters around. And we could rewrite this. Actually, let me rewrite it just for fun. I could rewrite this over here as 2cb, not rewrite it, I can swap the letters, times the cosine of a. So here I'm swapping the a's and the c's, is equal to c squared plus b squared minus a squared. There's nothing unique about the side c. I can do this with all of the sides. So here, when you have a big C here, you have an a and a b out front, and then you have the a squared plus b squared minus the small c squared. If you have a big A, then you're going to have the CB in the front, and then you're subtracting the a squared right over here. And this is useful because this term right over here, looks almost like this term over here if we could just multiply this by b. So let's do that. We can multiply that by b. In fact, let's multiply this whole numerator, this whole term by b. So if we multiply this whole term by b, what do we get? We get a b there, we get a b there. And of course, you can't just arbitrarily multiply an expression by b. That'll change its value. So what we can do is multiply the expression by b, which we just did. We distributed the b across here. But then we'll also divide by b. So I'll divide by b. That's equivalent of multiplying the denominator there, not b squared. That's the equivalent of multiplying the denominator there by b. That's the same thing as dividing by b. We've multiplied by b, divided by b. Or that's the same thing as just turning this into b squared. Now, what does this give us? Well, we have this term right over here. This term right over here is now the exact same thing as that over there. So it is now a squared plus b squared minus c squared. And then this term right over here is now the exact same thing as this thing over here, which is the same thing as that. We're using the law of cosines. So this is plus c squared plus b squared minus a squared. And then all of that times this, sine of b, sine of capital B over b squared. Now, what does this give us? We have an a squared and a negative a squared. Things are starting to simplify. A squared, negative a squared. We have a negative c squared and a positive c squared. So what are we left with? We're just left with a 2b squared. So our whole expression has simplified to 2b squared sine of b, sine of capital B, over lowercase b squared. These cancel out. So our whole expression simplifies to 2 sine of b. And from the get-go, we knew what b was. We know it's 60 degrees. So this is equal to 2 times the sine of 60 degrees. And if you don't have the sine of 60 degrees memorized, you can always just break out a 30, 60, 90 triangle. So let me draw. This is a right triangle right over here. This is 60 degrees. Hypotenuse has length 1. We're dealing with the unit circle. This side is 30 degrees. The side opposite the 30 degrees is 1/2. The side opposite the 60 degrees is square root of 3 times that. So it's square root of 3 over 2. You could even use the Pythagorean theorem to figure out, once you know one of them, you could figure out the other one. So it's the sine is opposite over hypotenuse. So square root of 3 over 2 over 1. Or it's just square root of 3 over 2. So this is equal to 2 times, this is a home stretch. It's very exciting. Square root of 3 over 2. These cancel out. So we are left with the square root of 3. That's a pretty neat problem. And just in case you're curious, this came from the 2010 IIT. IITs are these hard to get into engineering and science universities in India, and they give you this exam to like hundreds of thousands of kids, and the top I don't know like 2,000 actually get into one of the IITs. But anyway, I just thought it was a pretty neat problem.